Hello, this is Dr. Hanaa Assil, and this is a review on the modular system of the IGCSE chemistry at Edexcel. The new modular system has divided the syllabus into 2 units. So there is Modular Unit 1 and there is Modular Unit 2. So we would like to revise the topics that are included in each unit. So according to the new syllabus, the Modular Unit 1 includes all of these: states of matter, elements, mixtures, compounds, atomic structure, periodic table, chemical formula and equations and calculations, reactivity series of metals, extraction of metals, acids and bases, salt preparation, energetics. Organic chemistry in this first unit includes only alkanes, alkenes, and fuel or crude oil. So these are the topics that will be included in the paper on Modular Unit 1. So let's quickly revise all of these chapters. So the first chapter, you should remember states of matter, solid, liquid, gas. We've revised all of this before. When we talk about arrangement of particles, in solid, it is regular rows, close packed. Liquids, random arrangement, near each other in clusters. Gas, random arrangement, far apart. If we're talking about movement, and please pay attention, is the question asking about arrangement or movement? So when the question asks about arrangement, do not talk about movement. But when we're asked about movement of the particles, in a solid, they vibrate in fixed position. In liquids, they move around each other, so we call that also a random movement. Gases, fast, free, random motion. Which of these has more energy? You should remember that as we go from solid to liquid to gas, the gas has the most energy. Which one is compressible? You know that the gas is compressible because the particles are originally far apart, so you can press them together. Which one has fixed volume? Solids and liquids have fixed volume. Which has fixed shape? Only the solids. So this is basic chemistry. Change of state, you should know the meaning of each, or the name actually, and the meaning of each change of state. So going from solid to liquid, it's melting. So what is meant by melting? Change of state from solid to liquid. When we talk about the temperature at which this happens, that is called the melting point or the melting temperature. Remember that melting point is the temperature at which solid changes to liquid. If we're talking about from liquid to gas, that's boiling. So boiling is the change of state from liquid to gas. But you should remember that we have two things that are change of state from liquid to gas: boiling and evaporation. So distinguish between them. Boiling is the change of state from liquid to gas at a fixed temperature. The temperature at which that happens is called the boiling point or the boiling temperature. So this is the temperature, not the point. It's the temperature at which liquid changes to gas. And we said the difference between boiling and evaporation. Evaporation is again change from liquid to gas, but this is at any temperature. Boiling was at fixed temperature, and evaporation occurs only on the surface of the liquid. Please remember all of this. So going back from gas to liquid, condensation. So condensation is the change of state from gas to liquid, and in these cases please pay attention to the direction of the arrow. Going from liquid to solid, that is freezing. So freezing is the change from liquid to solid. Again, some substances go directly from solid to gas or gas to solid. That is called sublimation. Sublimation is the change from solid to gas or gas to solid without passing through the liquid state. So all of these changes of state, if I have a solid, I need to do what to change it to liquid? The solid is heated to change it to liquid. The liquid is heated to change it to gas. That means we're giving it heat. If you remember, a reaction that takes in heat is called endothermic. So melting and boiling are endothermic processes. Going the other way, gas going to liquid, we cool it. That means it gives out some of its heat. Liquid going to solid, it is cool. That means it gives out some of its heat. That is exothermic process. So condensation and freezing are exothermic. You need to know how to explain what happens during melting or boiling. If we're heating a liquid or we're heating a solid, what happens when a substance is heated? The particles gain kinetic energy, move faster, overcome the attraction forces between them, and move further apart. So they change from either solid to liquid or liquid to gas. The other way around, during condensation or freezing, the substance is cooled, so the particles lose kinetic energy, move slower, come nearer to each other. So they change from liquid to solid or from gas to liquid. So if we're asked to describe the changes in arrangement, movement, energy of particles when the liquid wax cools, for example, if any liquid is cooling, what is happening to the arrangement, the movement, and the energy? You should realize when we're going from liquid to solid, the particles lose kinetic energy. So that is the change in energy. They move slower, so that's the change in movement. And they come closer to each other and become a regular arrangement, and that is the change in the arrangement. Now you should know if something is a solid at room temperature, if we say a substance is a solid at room temperature, that means is the melting point high or low and the boiling point high or low. If it's solid, that means it has not melted yet, it has not boiled yet. So that means melting point and boiling point are higher than room temperature. If a substance is a liquid at room temperature, that means it has already melted. That means we have passed the melting point, so that means the melting point was low, but we haven't reached the boiling point yet because it has not evaporated. Now, if something is already a gas at room temperature, already a gas, that means it has already melted and it has already boiled, and that means it has low melting and boiling points. So if we're given melting points or of a substance, we can determine the physical state at room temperature. So if we're told that capric acid, for example, the melting point is 32, melting point is 32, that means that at room temperature we have not reached its melting point yet, so it's a solid. When we say formic acid, melting point is 8. That means at 8 degrees Celsius it has melted, so by the time we reach the room temperature it has become a liquid. Now we are told that the boiling point is above 100, so it has not evaporated yet, so it is a liquid. Now palmitic acid, for example, has a melting point of 63. Again, that means at room temperature we have not reached its melting point, and that means it is a solid. Diffusion, the process of diffusion is movement of particles from an area of high concentration to an area of low concentration down the concentration gradient. What is concentration gradient? It's the gradual change in concentration from where there is a lot to where there is less. So if we have some bromine liquid at the bottom of the jar, after some time all the jars, the two jars, will be filled with brown gas. Actually, what happened to the bromine liquid is that the particles of the liquid gain kinetic energy, move faster, overcome attraction forces between them, and move from area of high concentration to area of low concentration by the process of diffusion. So after some time, all of the two jars is filled with bromine gas. Now, which particles move faster or which particles diffuse faster? We said if we have ammonia particles on one end, HCl particles on the other end, then each of them will move from where there is lots of the ammonia to less, and where there is lots of the HCl to less, and somewhere they're going to meet. So if they're moving at the same rate, they should meet at the middle, but actually they don't, and that is because particles will diffuse faster if they are lighter. So which ones are lighter? If you calculate the MR, or the molecular mass of nitrogen plus 3 hydrogens, that's a total of 17. But HCl, the chlorine alone, is 35.5 plus 1, that's 36.5. So HCl is heavier. It will move slower. The ammonia has lower molecular mass, diffuses faster, and that's why they meet nearer to the HCl. Now, another factor is if I warm up this tube at higher temperature, the particles gain more kinetic energy, so of course they will move faster, and therefore that white cloud of ammonium chloride will appear faster. Another factor is the medium. So remember that if we have diffusion of substances in a gas, it's faster than in a liquid. Remember, no diffusion in solids. So if we have this, we have again ammonia on one end and the HCl on the other. Which line shows where the white solid is formed? Of course, we said it is formed nearer to the HCl because the HCl particles are heavier, higher molecular mass, diffuse slower. Another thing you need to know is the experimental techniques. You should know, first of all, the names of the apparatus. So that apparatus on top is called a dropping funnel, where we add something to the conical flask. There is a delivery tube going from the flask to the trough. Remember that big basin of water that we use in the setup is called a trough. And a gas jar is what is very similar to a measuring cylinder, but there is no graduations. So what is A? Again, A is a dropping funnel. B, a conical flask. D, okay, that's a gas jar, and D is a delivery tube. Again, what's that thing on top? This is another kind of funnel. It does not have a tap. Remember, the one that had a tap was dropping. This one, no tap. This is called thistle funnel. This again is called a flask or a round bottomed flask. This piece of wire on which we put the flask is called the wire gauze. That of course is a Bunsen burner, and that three-legged metal is called a tripod stand. That tube going from one part of the apparatus to the other is called a delivery tube. This, we said, if it has graduations, it's called measuring cylinder. No graduations, it is called a gas jar. And we said that big basin at the bottom is called a trough. This is where we can collect gases. So this is a setup in which we can collect a gas. Safety precautions. You will be required to state safety precautions. The safety precautions depend on what we're working with. So if we're working with an alcohol or anything that's flammable, so you should remember alcohols and organic liquids are flammable. So the precaution would be heat in a hot water bath, or do not put the alcohol near an open flame. If the experiment produces gases, we should say do the experiment in a fume cupboard. If we're working with something hot, we should say hold the hot objects with tongues or wear gloves. We are also required to wear safety glasses to avoid splashes in the eyes, or wear gloves if we're handling corrosive substances such as acids or bases. Okay, sometimes we're required to improve the accuracy of our results. What can we change to improve the accuracy of the results? Well, if we took the result only once, we took the reading only once, we should say, well, repeat the reading 3 times to obtain the average. What if we are measuring volumes of liquids? We said we should use a burette instead of a measuring cylinder. So if the experiment says they measured the volume using a measuring cylinder, then the improvement would be use a burette. It is more accurate. What if we're measuring volumes of gases? We said we should use a gas syringe because it's more accurate. So the gas syringe is used to collect the gas and measure its volume. If we're working with experiments that are measuring temperature, so something is giving out heat or taking in heat and we're measuring initial and final temperatures, we said the experiment should be done in a polystyrene cup. So if he says he did it in a glass beaker, that's not good. We should say use a polystyrene cup because polystyrene is an insulator, so there is less loss of heat to the surroundings. When we want a dry solid or a dry crystal, we say dry between filter papers. We don't say dry the crystals in an oven. So if we have crystals, dry between filter papers, not in an oven, because if we put it in an oven, this could cause decomposition of the substance or loss of water of crystallization if it is a hydrated. So when drying a gas, we say pass the gas through concentrated sulfuric acid. So if he says the gas was passed through concentrated sulfuric acid, why? Suggest a reason. This would probably be to dry the gas, but we don't use it for ammonia because ammonia, of course, is a base, so it would react with the acid. Or we could say pass the gas through anhydrous calcium chloride. Remember that anhydrous calcium chloride is a drying agent in order to dry the gas. Okay, when drawing a graph, we said we plot the points using small x's or a dot with a circle, not just a dot. And if there is a point away from the graph, we do not include it. So your graph should not be going in and out like that. It should be a smooth curve. And that means that that point that's away from the graph is referred to as an anomalous result. So something went wrong with the experiment and that result is wrong. Testing for solids solutions, of course, if we're told that a solid is colored, then it probably has a transition metal. If it is something without a transition metal, then it would be a white solid or a colorless solution. When a solid is heated and condensation forms at the top of the tube, we say this solid was a hydrated salt. That means it had some water with its crystals, which is called water of crystallization. How do we collect gases? If the gas is insoluble in water, the easiest way would be to collect it over water. So when a gas is collected over water, that's an indication that the gas does not dissolve in water. If a gas is lighter than air, ammonia, for example, dissolves in water, so I cannot collect it over water, so I need to collect it in a gas jar, but ammonia is lighter than air, so we call this upward delivery. The gas goes up and displaces the air in the gas jar. If the gas is heavier, then we collect it by downward delivery. If we want to collect the gas and measure its volume, then we have to use a gas syringe, and this is the kind of setup. If we're measuring temperature and we're told that the temperature increases or decreases, well, then we're talking about an exo or an endothermic reaction. So if the temperature decreases first as soon as the experiment starts and then continues to go back to room temperature, that means the experiment was endothermic. If the temperature, as soon as the experiment starts, the temperature starts to rise, and then at some point the experiment finishes, so the temperature returns back to room temperature, that is an exothermic reaction. So remember that whether the temperature goes up or goes down, that depends on whether it's endo or exo, but eventually either way the temperature will return back to the original room temperature because the reaction has finished. Reading a stopwatch, we know that what is inside is minutes and what is outside is seconds, and they usually indicate that. And what we do is we need to see how many minutes, how many seconds, and usually we are required to put this in a table in the form of seconds. So we need to change the minutes and seconds to a total number of seconds. Elements, compounds, and mixtures, you have to remember, you probably have seen this before, an element contains only one type of atom. So all the atoms are the same, whether we're talking about an atom of a molecule, so we just have individual atoms, or molecules of an element in which we have two atoms bonded together. But in both cases, if all the atoms are the same, then we're talking about an element. So helium, oxygen, anything in the periodic table is an element. A compound, you have to know, made up of two or more elements chemically combined together in a fixed ratio. I'm going to remind you again, if something is made up of two or more atoms, it's called a molecule. One is an atom, two or more bonded together is a molecule. So these are molecules of a compound if the elements are different. Water is a compound, methane is a compound, and so on. Mixture is made up of two or more substances added together, so they can be elements, compounds, atoms, molecules. They're added together and they can be separated easily. That is a mixture. So solutions are mixtures, and a solution is a mixture of solute dissolved in solvent. The solute is the substance that dissolves. So here, for example, it could be the sugar, that's the solute. The solvent is the substance in which a solute is dissolved, so that's the water here. And you should know that when we dissolve a substance in water, for example, we keep adding solid stirring until no more can dissolve. In that case, we have made a saturated solution. So a saturated solution is one in which no more solute can be dissolved at a certain temperature. Remember that different temperatures will dissolve different amount of solids. So a saturated solution is one in which no more solute can be dissolved at a certain temperature. Now we know that substances are either pure or impure. The pure substances are either elements or compounds. The impure are usually the mixtures. So mixtures are impure substances. A pure substance is something that has no impurities, nothing added to it. And you should realize that a pure substance has a fixed, sharp melting point and a fixed sharp boiling point. What if it has impurities? The presence of impurities will lower the melting point and increase the boiling point, so that an impure substance will melt at a temperature slightly lower than its melting point, and it will melt over a range, not at a fixed temperature. If we have impurities in a liquid, it will boil at a temperature higher. So impurities lower the melting point, increase the boiling point, and the impure substance melts or boils over a range, not at a fixed melting point or boiling point. We need purity in our foodstuffs, in whatever we eat, in our drugs, and that's the medicines that we take, in our drinking water. All of these should be pure. Solubility of a substance is the mass that dissolves in 100 grams of solvent at a certain temperature. That's the definition of solubility. How much of this substance will dissolve in 100 grams of water, for example, at a certain temperature. Remember, 100 grams of water is the same as 100 centimeter cubed of water, because density of water is 1. So solubility is the amount that dissolves in 100 grams of the solvent at a certain temperature, because different temperatures, different amounts will dissolve. So you have a curve like this, and you will be required to analyze it. How much of solid A dissolves at a certain temperature, for example, and so on. That is called a solubility curve. So when we have something like this, we have this curve. This is the mass of potassium nitrate that dissolves at a certain temperature. And remember that the graph is solubility in 100 grams of water. Now the question here says how much will dissolve in 50 grams of water at 35 degrees Celsius. So first of all, we look at the graph. 35 degrees Celsius, what dissolves from the graph is 56, but this is 56 in 100 grams. We are asked for how much will dissolve in 50 grams. That would be half of that. So remember that these solubility curves are solubility of a substance in 100 grams of water at different temperatures. How do we separate mixtures? Well, if we have something that is insoluble, we should be able to do filtration using filter paper and funnel. So if we're trying to separate a solid from the liquid, filter through filter paper and funnel. Remember, when you tell someone to do it, you're telling him to filter. The process is called filtration. What goes down in the conical flask is called filtrate. So filtrate is the liquid that goes down in conical flask. But when we're saying do something, we do filter. Filter through filter paper and funnel. So a question like this, which substances can be separated by filtration? Remember, we want something that is insoluble in water. So I need insoluble solid in water. That will be by. Okay, what if I have a solution and I want the solid that is dissolved in the solution? So we're trying to get crystals from a solution. What we do is crystallization. So the first thing we do is heat to point of crystallization. Then we cool to form crystals. Once the crystals are formed, then we filter the crystals through filter paper and funnel. The solution will go down as filtrate, and the crystals will remain in the filter paper as residue. So we wash the residue with a few drops of distilled water to remove any soluble impurities, and then we dry the crystals between filter papers. This is how we do crystallization, to obtain solid from a solution. Of course, to know the point of crystallization, we can insert a glass rod and remove it. Crystals should form on the tip. Okay, what if we need the water from the solution? So I have a solution, but I need the water, not the solid. We said if I need the solid, we do crystallization. But if I need the water, we do simple distillation using this kind of setup. Of course, the condenser is to cool and condense the vapor. And remember that the cold water in the condenser, it has to go in from down and out from the top. This is to fill the condenser for more efficient cooling. And of course, we have the thermometer to measure the temperature. If we have two or more liquids and we're trying to separate them, then we do fractional distillation. So fractional distillation is to separate liquids, and we're separating them based on the fact that they have different boiling points. So the property that they have that we are using is the fact that they have different boiling points. Of course, the liquid with lower boiling point will go up through the fractionating column, through the condenser that will cool and condense the vapor, and then it will be collected in this beaker. Remember that during the time we're collecting a certain liquid, the thermometer temperature remains constant. So if we are separating water and ethanol, ethanol comes out first. So while the ethanol is coming out, the temperature remains constant. How do I know that all the ethanol has been collected? When the temperature starts to rise again, then we remove this beaker and put another beaker. So each liquid collected at a certain boiling point is called a fraction. So if I collect the ethanol first, that's one fraction. Then I collect the water at 100 degrees, that's another fraction. So each fraction is a collection of liquids having similar boiling points that are collected together. Another method of separation is paper chromatography. And we use paper chromatography to determine number of components in a mixture and identify the components. So I have a sample. I want to know how many dyes, for example, in the sample, and which substances. I can use the paper chromatography. So we put a spot of the sample on a baseline near the bottom of the rectangular chromatography paper. Put the paper into a beaker containing a small amount of solvent. Allow the solvent to move up the paper. As the solvent moves up the paper, the components start to separate based on their solubility in the solvent. So the one that is more soluble will go up, the one that is less soluble will go down. So what we do is, again, put a spot of the sample on a baseline near the bottom of a rectangular chromatography paper. Place the paper in a beaker containing a very small amount of solvent. Usually our solvent is water. If we are required to suggest another one, it is ethanol. Allow the solvent to move up the paper, and this will separate it into different spots. Remember, the baseline is drawn in pencil because it doesn't dissolve in the solvent and will not interfere with the experiment. The baseline has to be above the level of the solvent. So the solvent, if we're required to draw the level of the solvent, it has to be below the baseline to avoid dissolving the spot in the solvent. Now, when the solvent moves up the paper, it separates into different spots based on solubility in the solvent. So the one that is more soluble goes up, the one that is less soluble does not go up that far, and anything that remains on the baseline is insoluble in water. So a compound that does not move up with the solvent is not soluble in the solvent. When substances are separated, we can compare them to other substances any spots that go up the same height are the same substance, and they will have the same RF value. Now, how do we calculate RF value? We said RF value of a spot, for example, that red spot on the right, substance 3. I want to get its RF value. We measure from the baseline to the middle of that spot, divided by from the baseline to the solvent front. Solvent front is where the solvent went up in the paper. So the RF value is the distance moved by the spot divided by the distance moved by the solvent. And the relative RF values are an indication of how soluble the substance is in the solvent. So if something has a high RF value, remember the maximum RF value would be 1, because this is distance of spot over distance of solvent. So if it is about halfway through, it could be 0.4 or 0.65. If it is further up, higher RF value, 0.8, 0.9, that means it went up in the chromatography paper. Now, if spots are not colored, so if we're doing paper chromatography of something like sugars, maltose, sucrose, fructose, or amino acids, these are substances that are not colored. So when we put spots on the baseline and we put it into the beaker, we really don't see anything. As the solvent moves up, we're not seeing anything. But then once we have finished, we can bring out the paper, allow it to dry, and spray with a locating agent. A locating agent is a substance that gives the spots color and makes it visible. So when we have spots that are not colored, we spray with locating agent to give the spots color and make it visible. So if we have different spots like this and we're trying to compare them, which dye is present in P, you should realize that the one present in P is the one that has a spot the same height as a spot in P. So that means P contains substance B and something else, which we don't know. Usually you will be required to plan an investigation. An orange drink may contain artificial colors, which he calls E110, E129. Plan an investigation to determine the presence of these colors in a sample of orange drink. So for this, we need to explain chromatography. So how do we do chromatography? Put a spot of the orange drink next to a spot, because I'm trying to determine if it has E110 and E129. I put a spot of the drink next to a spot of each of these on a baseline near the bottom of a rectangular filter paper, or you could call it a chromatography paper. Put the paper into a beaker containing a very small amount of water. Allow the water to move up the paper. If the orange drink has spots the same height as the artificial colorings, then the coloring is present. This is how you plan an investigation. Another type of questions, if he's given you all the options and he's saying which of these methods do you use to obtain sand from sand and water. Sand and water, sand dissolves, water is something that does not dissolve the sand. So I have sand that is insoluble, I can do filtration. To separate crude oil, you should remember crude oil is petroleum, it's actually a mixture of liquids, and we said to separate a mixture of liquids, fractional distillation. To obtain pure water from seawater, we said if I have a mixture and I want the water, simple distillation. To obtain ethanol from a mixture of ethanol and water, again ethanol and water are a mixture of liquids, fractional distillation. Good. Now, do you remember about atomic structure? You should remember that the atom has a central part which is called the nucleus. The nucleus contains neutrons and protons. Both neutron and protons are referred to as nucleons. So nucleons is anything inside the nucleus. Electrons are revolving in energy levels around the nucleus, and you should be familiar with the mass and the charge of each of these, what we call subatomic particles. So you should know that neutrons and protons each have a mass of 1, but the mass of an electron is something very, very small. We give it as 1 divided by 1840. This is actually a very, very small number, 0.0000 something. So 1 over 1840, the mass of the electron, it's very, very small. The charge, we said, the neutron is neutral. It doesn't have a charge, so the charge is 0. Protons have a charge of +1. Electrons have a charge of -1. Please remember all these basics. Atomic number, again, atomic number is number of protons in the nucleus. So which one is the atomic number? When you look at the periodic table, the smaller one is the atomic number. So that is the number of protons. If we're told what is meant by atomic number, it's number of protons in the nucleus. But in an atom, the number of protons is the same as number of electrons, so that is also the number of electrons. And you should know that because protons are positive, electrons are negative, and the atom has equal number of protons and electrons, so the atom overall is neutral. So atoms are neutral because the number of positive protons is equal to the number of negative electrons. Mass number, we refer to it as atomic mass, or we could refer to it as nucleon number because it is the number of both protons and neutrons in the nucleus. So the mass number, or the nucleon number, is the total number of protons and neutrons in the nucleus. Looking at the periodic table, it is the bigger number in the periodic table. And remember, if I have atomic number is, for example, 13, mass number 27, and we said atomic number is number of protons, mass number is protons plus neutrons, then the number of neutrons is the difference between the big number and the small number, the difference between the mass number and the atomic number. How do we distribute electrons? Remember, we have energy levels. The first energy level nearer to the nucleus can take only 2. And the next shells can take up to 8. So if I'm trying to draw electron configuration of aluminium, it has a total of 13 electrons. The first shell takes 2, the second shell takes a total of 8, and I'm still left with 3. They go into the third shell. So if the question says draw, then you're going to draw these circles around the nucleus with the dots to indicate the electrons. But if we're told to write the electron configuration, we just write 2, 8, 3. So potassium, again, potassium, I look at the periodic table, it has an atomic number of 19. That means the first shell takes 2, and then 8, and then 8, and then 1. So this is the distribution of electrons, or what we call electron configuration. But an atom can lose or gain electrons. So if the atom, sodium for example, anything in group 1, 2, or 3, has a small number of electrons in the outer shell, we know that anything in group 1 has 1 electron in its outermost shell. So sodium, if we distribute the 11 electrons, I have 1 at the end, I can lose it. And when we lose electrons, we become positively charged. So a sodium atom loses 1 electron, it becomes positively charged because originally it had equal number of protons and electrons. So if we say atomic number is 11, then it has 11 protons, 11 electrons, so the overall charge is 0. But when we lose 1 of the electrons, now we have 11 protons which are positive, 10 electrons, that means I have 1 extra positive charge. This is called a cation. Please remember that a positively charged ion is referred to as a cation. or atoms of nonmetals. Nonmetals have 7, 6, 5 electrons in their outermost shell. Now, a nonmetal needs to gain electrons. So an atom like fluorine has fluorine has 9 protons, 9 electrons, no overall charge. But if it gains 1 more electron, so that instead of 287 it's now 288, now it has an extra negative, so this is a negatively charged ion. Please remember, negatively charged ions are called anion. So if I have normal fluorine with atomic number 9, mass number 19, the number of neutrons, how do we get it? The difference between 19 and 9. Number of protons is the atomic number, number of electrons is the atomic number. Distribution of the 9 electrons would be 2 in the first shell, 7 in the second shell. But if I have F minus, what does F minus mean? You should remember that F minus means I added an electron. Number of neutrons is the same. Number of protons never change. Number of electrons, now I have 1 extra, so now it is 28. Again, aluminium has atomic number 13, mass number 27. Number of neutrons, the difference. Number of protons, the small number, atomic number. Number of electrons, atomic number. Distribution of 13 electrons, 283. What if I have aluminium 3 plus? What does 3 plus mean? It means it has lost 3 of its electrons. Number of neutrons is the same, protons is the same, but now I have lost 3 electrons, so now it is 28. Please remember all of this. Isotopes are atoms of the same element having the same number of protons but different number of neutrons. So isotopes, same number of protons, same number of electrons, but different number of neutrons. So if we have this kind of diagram, what is the atomic number of this atom? Remember, atomic number is the number of protons. So obviously that diagram or that atom has 3 protons. What is the number of shells? The shells are the circles around the nucleus, of course. These have 2 energy levels or 2 shells. What is the mass number of the atom? How do we get mass number? Mass number is the total number of protons and neutrons. So we add up everything in the nucleus, that is 7. What is the number of protons in an isotope of this element? Remember, all isotopes have the same number of protons. So an isotope would have the same number of protons. Relative atomic mass is the average of the mass number of the different isotopes in the ratio of their occurrence. Remember that the masses of all atoms are relative to the mass of what? Relative to the mass of an atom of carbon-12. So if I have different isotopes, so I have chlorine with a mass number 35, 75% of the atoms has this mass, so we say it has an abundance of 75%. The chlorine atoms with mass number 37 have an abundance of 25%. I can use this to calculate the overall atomic mass of chlorine. We say the mass number times abundance plus mass number times abundance over the total abundance, which is 100, and that is why the mass number of chlorine in the periodic table is 35.5. Again, if we're given different isotopes with different mass numbers, the relative atomic mass is mass number times abundance, mass number times abundance, plus mass number times abundance. Now, please note that these questions, usually it says give your answer to something. So either 1 decimal place or a certain number of significant figures. Please make sure that you give the answer as. Okay, we're going to stop here in this part. So this is the first part of the modular unit 1. Please follow in the next parts. We will continue the syllabus of Modular Unit 1. Thank you.